this is part 3 of 5, which is all about using atmospheric models to do event attribution, and is the core approach we're taking in this workshop. So the approach we want is atmospheric modeling. So in that case, we carry out atmosphere-only simulations, and where atmosphere-only coupled to land surface models, where we carry out a set of simulations. So we have basically two sets: a historical ensemble, that's a model driven by current sea surface temperatures, sea ice, greenhouse gases, anything else we think is important, and then a natural ensemble, where the model is driven with pre-industrial greenhouse gases with a human contribution to sea surface temperatures and sea ice removed, and any other human drivers. So, for example, we might remove ozone or aerosols or so on. And then we use these simulations to estimate the probability of events. So we could then look at the two simulations. So for the event we are interested in, what is the probability of exceeding our key threshold? So these condition on the climatic conditions at the time of the event. And in particular, as we know that, say, El Nino and changes in the North Pacific and the ocean temperatures are really important across the tropics and actually into China and bits of North America. Europe isn't particularly affected by El Nino, so it matters less. That might be important. So we might want to talk about what was the risk of a particular event in this year. And that's where that helps us. So we can then use that to run multiple simulations for the year in question, which allows us to increase the signal to noise for rare events. We can also run at higher resolution because we need less computation for the same amount of data. We don't have to run an ocean model than couple models. So we're more likely to capture the meteorological drivers of the extreme event. Again, that needs to be tested. We found that for cold extremes, there's no real evidence that across the CMIP archive there's any difference between higher resolution and lower resolution. And we're actually finding that for extreme precipitation on sort of 2 by 2 degree scales. So it may not be true, but more likely. Atmosphere and ocean simulations, though, do not represent ocean-atmosphere coupling at all, so they may misrepresent important events. So if, for example, if we could simulate hurricanes well, and we can't until we get down to 20 kilometre resolution or so, maybe even 10, part of an important thing about a tropical cyclone is it drags a cold wave behind it, so it pulls it up, so you can see those interactions might matter quite a bit. And we also need to remove the human contribution to sea surface temperatures and sea ice, which can be a bit arbitrary and is another source of uncertainty which we might need to consider. And some papers have done that. So their approach to generating pre-industrial sea surface temperature and sea ice data sets, which is what we need to drive these models. You don't need to do this. We've already done it for you and ran the models, thanks to Fraser at the Met Office. But there are several different approaches to doing that. The general approach is to use signals derived from coupled climate models to estimate the low frequency, so the decadal and beyond timescale, human-driven changes in sea surface temperature and sea ice. These changes are quite sensitive to the model and the simulated climate variability in the models. So there's a sense in which we don't quite sample it. There are available data sets that if you want, that you can use to see the impact of this. Having estimated this, we remove it from the observational record to essentially naturalize the world. So the general approach then is, given an ensemble of simulations and essentially the magnitude of the event in the model simulations, we can then use that to estimate parameters for probability distribution. We're just comparing events for the same year. We don't need to worry about time dependence. If we wanted to look across a long range of time and do some more advanced fitting, we would need to think about time dependence and covariates essentially in the drivers for probability distribution. But at the moment we don't. So which distribution? Well, it depends on your problem, actually. So if you're thinking about long-lasting temperatures, then a normal or Gaussian distribution is most appropriate. Daily extremes, generalized extreme values, likely appropriate. In between, well, beta distributions pop up or other distributions. And it does depend on your problem. My advice for doing that is, having figured out what your extreme event is, that literature is probably a good guide to the class of distributions you should attempt to fit. Having got those distributions, you can then determine the probability of being greater than threshold for both model ensembles, and then from that easily compute the risk ratio. So that's the basic idea. With a limited sample of data, the risk ratio is uncertain. That is, if you had a different set of realizations, you might get different answers. And this is particularly true when events in one of the ensembles are rare. So if they're very rare, you have very few samples, and so your probability distribution estimates relevant to those extremes are rather uncertain. So the easy approach to do this is to use bootstrapping on the data used to fit the distributions. And bootstrapping is sampling with replacement. So you have your population of numbers and you pull out with replacement, refit the distributions, recalculate the risk ratios. My experience is 1,000 replications is likely enough. If you see this article here, and don't worry, the slides are going to be available as well, you can go and have a look at that approach. Okay, so model reliability is really important. So estimating these probabilities makes an extremely heavy use of models. There's very little observational constraint at this point in this. Minimum we need to do is correct model biases. So for rainfall, we might rewrite everything as sort of percentage of normal. For temperature, we might think about it as anomalies, differences from normal. And even so, how do we know that the model is reliable is an important question. And it depends on the event, and it needs scientific judgment. So your knowledge about the circulation relevant to your event is important, or the literature that tells you about that. So you'll need to consider this in the workshop. And so the first question here, when the workshop, we can't consider it in a huge amount of detail, and given the sort of expected output from you, you just don't have space to do very much on it. But think about the main meteorological drivers of your event. Ask, does the model simulate those well? And you might be able to tell that from the existing literature. And then think about what is causing the change in risk. So is it that the model distributions are getting wider, or are they just shifting? Shift is probably more reliable than a widening of the distribution. So here's an example study from the 2016 workshop. Now I'll say at the time they didn't really study the mechanisms. We have subsequently done that, so I'll show you that. So here's a discussion of the event. Here's a land surface temperature anomaly, similar data being used as used in the Russian study. So here's a cold surge that struck most of East Asia, had large social and economic impacts. It brought snow to Shanghai and down, actually, I think as far south as Guangzhou. In fact, I remember, I think I was going to a meeting in Beijing and for some reason had to fly through Guangzhou. Colleagues, and it was pretty warm relative to Scotland, but colleagues of mine who were coming through Shanghai had quite a hard time. Anyway, this cold surge had large social and economic impacts. So the minimum temperature in Inner Mongolia fell to a record low of minus 46.8 degrees centigrade on 23rd of January. The minimum temperature in Shanghai fell to minus 7.5 centigrade. Even Hong Kong, it's down here near Guangzhou, was 3.3 degrees centigrade, and that was the coldest temperatures of the last 60 years. So we certainly had unusually cold conditions in January, cold air coming out of that. So a question, you could imagine all kinds of ideas about why climate change might be impacting that. So that's essentially what the aim of the study was. So here's a picture of the station data. Here's the cold regions. These are anomalies. So you can see, particularly down in southern China, we're getting temperatures below down to minus 8 to 10 to 12, even in some places 12 degrees below normal. Here's where the record breaking was set. So reds are the first coldest, greens are the second coldest, and blues. You can see several stations set their record in back to 1960, which is when reliable observations from China are available. And the participants selected this box here as the region of interest. They're focusing only on mainland. And here is the average temperature for this pentad. So I think they were a little bit over precise on the pentad, but here we see the anomalies. So you can see, like back in 1960, -2. Here's a very cold event in 1984, which was the second coldest. Here's the 2016, so definitely the coldest on event. And the trend in this is actually quite small. It's warming at about 0.078 degrees centigrade per decade, 0.1 of a degree centigrade per decade, which is considerably less than the global average. So there may well be a weaker climate change in this region going on. And then they fit two distributions to the data. So they fit GVs, so they look quite Gaussian. Here's our 2016 threshold. Here's our historical ensemble. Here's our natural ensemble in green. The probability of having temperatures below this 2016 threshold, -4, it's about 7. In the natural, it's about 7%, 7.3%, while in the historical world, it's about 3. So we don't get rid of the probability of those happening. So if P1, and so the risk ratio is 0.42. So what that said is that anthropogenic influences are estimated to reduce the likelihood of an extreme cold event with an intensity equal to greater than this record in 2016 in eastern China. Note, very careful language. That's what you expect from peer-reviewed literature, by 58%, i.e. basically reduced by 60%. It's my kind of order of magnitude estimate. So there's a sense, so as you'd expect, and it looks, what's the largest cause? It's essentially a shift. The historical world is warm relative to the natural. Here's another way of looking at it. Here's the return period. So here's the historical, there's our threshold. Here's the natural. So in the historical period, it's essentially a 1 in 30-odd year event. In the natural world, it'd be a 1 in 13-ish year event. And you can see actually quite dramatic shifts between here and here. So return period has been extended by about 20 years. So it's become quite rare as opposed to not uncommon. And then here's some model evaluation, which we just did more recently. We've done that using CMIT5 and CMIT6 ensemble. That's a paper published by Tett et al. In JGR. Here's the GUI. You can just pick that up again, look at the slides. So this shows what average cold events look like in era 5. So this is the surface temperature on the left. Contours are showing the shortwave radiation. So we've got a big decline in shortwave radiation in the coastal bits of southern China. Temperatures are about 4 degrees colder than normal. Here is what it looks like in CMIT5, and here is what it looks like in CMIT6. I think the main difference that shows up is less difference in the shortwave radiation. So this is negative in the reduction in shortwave radiation. Here's what the pressure system looks like at 500 hectopascals. So we have essentially lower regions over here. And CMIT5 and CMIT6 are again quite similar, and they're not too different. And then we in this case, we essentially just use Taylor diagrams. If you're not familiar with Taylor diagrams, they're essentially a measure of the correlation around here and the standard deviation of the sort of field differences here. So here's all the models. The red dashed line shows that if they were if they were within agreement within era 5, this is where we'd expect them to fall based on their variability. So you can see this pressure differences. Pressure fields are in fairly good. Surface pressure fields are in fairly good agreement. So is T2M, though a little bit further away. So they're wrong in some sense. Said 500. We didn't have enough statistics to do the differences, but again, you can see they're not bad, but still some room for improvement. And here's the radiation term, which I think is actually quite poor, but again hard to tell because we don't have enough data to do the work out where this red dashed line should be. So that's a kind of simple way to do some evaluation of the model. So in summary of the approach, so first of all, definition, define the event, consider impact to help you in doing this. And we have a bunch of work on what I might call risk ratio, which is about statistics, use large ensembles to generate samples of extreme events, fit appropriate distributions to data from each ensemble, compute the risk ratio, use bootstrapping to compute uncertainty in the risk ratio. And then a sort of final bit on credibility, understand the meteorological drivers of the extreme event. Does the model capture this? Ask what's causing the change in risk. And I think that's effectively the approach that we're going to support you to follow in this workshop.